Our final speaker tonight is the hometown guy. John Brennan is from McMaster. John's trying to find simpler ways to know if water is safe to drink or not. I don't think I need to explain any further about why that matters, given what we've seen happen in this province and around this country in the years past. John's research involves a bioactive paper. What is that? That is, it reacts to pathogens or poisons, making it cheaper and easier way to discover contamination. And naturally, what John will be arguing is what matters now is how safe our water is and how to test how safe our water is. Please help me welcome John Brennan.
Right. Well, thanks to everyone for making the trip to Hamilton, whether it was from near or far. So what I want to be able to sort of get across today is a little bit of the research we do, but also to try to give you a sense that while we're trying to make what might be conceived of as a very low-tech device, a simple paper test, in order to actually get that, there's a lot of very high-tech research that has to go into the front end of that. So I'm one of these poor guys who doesn't have a clicker, so I have to keep yelling next slide all the time. So next slide. All right, so this just gives you an indication of just a few of the problems that have occurred over the last decade in terms of water quality. So probably one of the most, I guess, memorable ones was the Walkerton tragedy. So this was an E. coli 0157 outbreak in the year 2000. A whole bunch of people died, several thousand people got sick, but there's a lot more to it than that. There's all kinds of problems, boil water advisories, there's issues in terms of the quality of beach water. How many times do you hear that there's beach closures because of E. coli? So this is a problem that has been around for a long time, and it's not one that's going away anytime soon. So next slide. If we want to ask how do we currently test our water, whether it's our drinking water or our beach water, the top shows a very basic test. It's basically a microbiological test to look at E. coli. So we have these little petri dishes and you see these little dots. So on the left you see a few dots. That water's not too bad, but it still wouldn't be drinkable. On the right you see something that's fairly contaminated. And this is how we currently do testing for E. coli. On the bottom, you see this great big device called a liquid chromatograph mass spectrometer. That's currently how we test for things like pesticides. So if we ask, why are these not good enough? Well, this takes 48 hours, lots of time. This, you probably don't have one of these sitting in your kitchen. I do, but most people don't. These cost a lot of money. So this setup's probably about $750,000. So what we want to do is get around the time and the money. And we took our inspiration, next slide, from this. So you can go into the drugstore today, or the pharmacy, and you can buy one of these. This is a home glucose test kit, or test meter, or you can buy one of these. So pregnancy kit, right? What these both do is they use a biological element, something called a protein, that is interfaced onto a surface. So what we need to have happen is you have to be able to take biology out of its normal environment, which is us, and put it into this very artificial environment onto some surface and keep it alive. So in this case, there's an enzyme called glucose oxidase, which when it binds to glucose, which is what we want to detect, gives an electrical current, and the current's proportional to the amount of glucose. This one uses something called an antibody. Antibodies are part of our immune system. This particular antibody binds to the pregnancy hormone, and within a couple of weeks of getting pregnant, what will happen is, not pregnant, 1 line, you get pregnant, 2 lines. Antibody flows along the surface, gets captured by a second antibody, and a little gold label gives you a color, little line. So how many other things can you go into the drugstore today and buy that will allow you to do these kinds of tests? Not many. So the reason is, as I said, it's very hard to keep biology active when you put it on an artificial surface. So how do we get around that? Next slide. And way down here there should be an arrow. There it is, and if we hit that, what you'll see is a robot. So this is how we do it. We make thousands and thousands of slightly different bio-inks that we ultimately can print. So we have a whole series of robots that do tasks for us, and at the end we find things that we can print using piezoelectric printing technology. So all of this gear is very, very expensive and complicated to use, but at the end of the day, what we do is by screening tens of thousands of different potential inks, we find the one that is printable, that will give a color change or an electrical signal, that will keep a protein active, that won't allow fouling, and all these things. So because we're asking multiple questions at the same time, by screening, we can get multiple answers. So once we've done this, next slide, the goal is to go from the millions of dollars to the $30. Actually, this one's probably closer to $100. It's really fancy. It's got, multiple cartridges. So what we've been doing is taking these inks that we can then put into standard cartridges, into standard inkjet printers, and print our tests. So we're looking at doing this in two ways. One way for the North American market is to go with a big printer and print lots and lots and lots of strips. One of the problems with that when you're talking about moving this into the developing world, so places like Kenya or India or France, is that what you ultimately get, is a stability issue. If we're going to try and put this in a warehouse in India where it's going to get to 50 Celsius for some length of time, biology will die. So one of the concepts we have is, why not print it on site? If we can make something where you now have the software, you have the ink, and you simply have a piece of filter paper you put through, you print your own tests. And voila, you can test your water. Next slide. So here's 3 examples of tests that we've developed in our lab. So this one detects organophosphates. So what's an organophosphate? Long ago, these were the pesticides that we used to spray all over our lawn. In the developing world, these are still used. They've been banned in North America for 3 or 4 decades, but these are widely used in the developing world. So what will happen is we import food from India, China. It's been sprayed with this. We can use this to test. Another thing that you will find is chemical warfare agents. So in Syria, there was a big issue with chemical warfare agents. These strips will detect those compounds directly. So we have the ability to detect these kinds of things with a simple test where we get a color change. This one detects heavy metals. This particular test is designed to detect mercury. And you can see that we get a nice color change. Both of these tests use an enzyme. This is a biological element that converts a molecule to something that, in our case, is colored. And in this case, the pesticide inhibits the enzyme. It's an enzyme called acetylcholinesterase. It's in your body. And what happens is if this gets inhibited, you go into neural shock. So this is how it actually kills you as a chemical warfare agent. Mercury, obviously bad. We have a different enzyme, gets inhibited by mercury. This one detects E. coli. And the key thing with all 3 of these tests is that they're able to detect these species, in these 2 cases, well below the regulatory limit. In this case, we can detect at the limit needed for beach water. We're working towards the limit needed for drinking water. Next slide. So we also have developed this fancy thing called the iPhone. I wish. But what we have done is we've developed an app for the iPhone. So this app allows us to take photographs anywhere that we want of our strips and ultimately quantify the color and convert that to concentration. So now you use something you already have to get your signal. And next slide, it geotags it. So now you go out in the field, you take a photograph of the strip you use in the field, and you then have, at McMaster, we have a website called WaterMap that this iPhone sends all the data back to. So we can now map the water, look at whether it's safe to swim, say, way up here in northern Quebec. I don't know, apparently not, it's red, that would be bad. Of course, around Hamilton, everything's red, I don't know why that is. But the idea here is that we can go and figure out the quality of water, map that, and do this in real time very, very cheaply. So last slide. Thank you for your attention. And this is why I think research matters.